Welcome back, and today we'll talk about technical prelims 2. This is a technical video, so it's all going to be about technicalities of Mathematica commands and some technicalities of programming. We'll not talk too much about physics and mathematics here. Today we'll talk particularly about for loop, or how to write a for loop in Mathematica, and we'll contrast and compare with table command. You're already familiar with the table command. If you want to generate a series of data, you can use table command. So table command sounds a lot like a loop, something that a loop will do for you. But for loop is something that is different kind of construct, and today we'll contrast and understand the difference between table and for loop. So let's go ahead and get started with it. To take this an example, I'll use something known as Riemann Zeta function. So I will use, I'll search about Riemann Zeta function, and notice the symbol over here. Let me type this out and show it to you again. If I type equal to once and then again type an equal to, this becomes an equal to inside a star symbol like this, and this becomes a natural language, Mathematica's natural language tool, where I can type something and Mathematica will search the internet in its own knowledge database and tell me about what that is. So here I've searched about zeta function or Riemann zeta function. Riemann zeta function is a famous function, and it's giving an interpretation here, assuming zeta function is referring to a mathematical definition, and it's giving you disambiguation over here. It says, it gives you a bunch of information about zeta function. If you're not familiar with the Riemann zeta function, don't worry about it. It's actually simply given by this series. So zeta of n is simply given by this series. It's an infinite sum of numbers. It's a sum over 1 over k to the power n, where k is sound from 1 to infinity. So zeta of n is summation k equal to 1 to infinity 1 over k to the power n. Mathematica has a built-in command zeta, so we'll look at zeta of 2, and zeta of 2 is a famous number pi square over 6. You can evaluate this numerically, and let me do that over here. Zeta of 2.0, the moment I put 2.0, Mathematica will interpret it as an approximate number and will calculate its numerical value, which is 1.64493. Now as a series, this is simply 1 plus 1 by 2 square plus 1 by 3 square and so on. That's the series we are talking about. Let's go ahead and calculate that and see if this gives me 1.64493, which is what zeta of 2.0 is. I see that this is away, so I may be tempted to add more terms to this to find out how quickly does it converge to that, and we see that we're not quite there, and we can keep on doing this manually, add one time after another and compute it, and we see that it's actually progressing very, very slowly. As I add another term, I see there's a small shift in pretty much the 4 digit or something, which is not impressive. I have to catch up to 1.64493. Of course, in order to get there, in order to get pi square by 6 exactly, I need to sum infinite number of terms, and that is something I'm not going to do manually, of course, and even computationally you cannot sum up to infinite number of terms, but you believe at some point, if you sum up large number of terms, at some point you'll get a very accurate number which is close to pi square by 6. To 6 digits of accuracy, it will be 1.64493. So in order to get that number, let's go ahead and calculate this by adding large number of terms. In order to add large number of terms, I need to produce this sequence. In order to produce this sequence, now you can see I have to do this many times. I have to do it large number of times, so I need to repeat something again and again, and at this point you would think that I should write a for loop. In order to write a for loop or some sort of loop, but rather than doing this with the for loop, first what I'll do is I'll do this with a table, which you're already familiar with. Table command is really interesting and powerful, so let's do this with table. So in order to do that with table, first what I'll do is I'll produce the sequence of these terms and then I'll sum them up. So simple algorithm, I'll produce a sequence to up to whatever desired numbers I want, and then I'll sum it up. Okay, so let's go ahead and produce this sequence. So table of 1 by k to the power 1 by k to the power 2 is what I want, because I want to calculate zeta of n over here. N is 2, so 1 over k square, and I want to sum k from 1 to, let's say, 10, and that's my sequence of digits. So it's inverse of squares, integer squares, and if I want to find the sum of all these terms, all I need to do is total the terms in this list. So the output of table is a list, and I want to add all the terms in the list, so I can go ahead and total them, and that's what I get. Mathematica goes and sums them up in a rational number form, but I want to see its numerical value, so I apply / n to it, and I'll get 1.54977. So that means 10 digits, 10 numbers are also not enough to reproduce this. So let's go ahead and increase that, maybe make it 100 this time and see what happens. Okay, I'm getting closer. Let me make it 1000 maybe. Good, I can match 3 digits, but I'm still not able to agree with 3 digits, and as it happens to be the case, it's 1 over k square, where k becomes progressively larger as I increase the number of terms in this series. 1 over k square is suppressed, and therefore this series progresses very, very slowly. It will take a long time or large number of terms to converge to this number 1.64493, and in this exercise we're exactly going to do that and find out. Let's try 10,000 terms. Okay, we are getting closer, but not quite there. First 4 digits agree in these two numbers, but not quite the 5th and the 6th digit. So in order to get that, let me go ahead and add one more 0 and see what happens. Oh, there we go. It's quite close. We are still away, not agreeing on the 6th digit. So let's go ahead and maybe put a 2 here. Wow, okay, there we go. So at least I need something between 100k and 200k terms in order to get the zeta function accurately to 6 digits. Very well. So it took us that many terms. Let's find out how much time does it take to do this computation. And Mathematica, you can do that by actually putting all of this thing inside timing. So doing / is same thing as wrapping the whole thing inside timing. So let me show that over to you over here. So I can go ahead and wrap this inside timing. When I do that, I'm going to get the list of 2 numbers. The first one is showing how much time did it take to compute this thing and the value of zeta of 2.0. So in order to compute zeta of 2.0 as a built-in Mathematica function, it only took 3 times 10 to the minus 5 seconds. This number is in seconds. So it took 3 to the power 10 to the minus 5 seconds to compute this number using the built-in function zeta. But if I use my brute force series or brute force sequence here, generate my brute force sequence to up to 200,000 terms, and then add all those terms, turn them into a numerical value, all of this is going to take me how much time? So to that I can add // which means whatever comes before this, apply the function timing on that. Applying the function timing on that, this is what I get. You see, it takes some time, and it takes about, on this particular computer, it takes me about 1.02 seconds to compute this number. So running this 200,000 iterations, it took me about 1 second to generate this number 1.64493. Let's go ahead and do this with the for loop. Of course, in table we generate a sequence, but in for loop I can iteratively add terms to whatever number of terms I want. So in order to write a for loop, I want to define my sum equal to 0. I want to initialize my sum equal to 0, and then I want to write my for loop, and I'm going to write the for loop here and also explain the syntax at the same time. So for loop has 4 arguments separated by commas. So let me put 3 commas. Each of these spaces will take in an argument for the for function. The first argument of the for function is initialization. In order to initialize something over here, I'm going to say n is equal to 0. I'm going to start with n equal to 0. That's my initialization. In the second argument of the for loop, I'm going to specify what is the condition on n. So n I want to run from n equal to less than equal to, let's say, 10. We'll make it 200,000 in a moment, but let me just limit this to 10. It's always a good idea to test out your loop for small number of terms. Once you know that's working fine, it's giving you results that you expect, then you can go ahead and run it for a longer duration. So I'm just going to constrain n less than equal to 10 over here. So n equal to 0 and less than equal to 10, that's my condition. I'm going to say increment n. That means after each round of running the body, executing the body, increment n by 1. So n plus plus means the same thing as n equal to n plus 1. So n equal to n plus 1 means increment n by 1, and n plus plus is a shorthand for that. It's also there in many other languages such as C and C++, and I'm sure many other languages use this notation. So we'll just use n plus plus. And now the fourth argument, which is the most important argument of the for function, is the body of the for function. What are you going to do in each iteration? So in the for function, in each iteration, I'm going to add to sum equal to sums in each previous value plus 1 by n square. In fact, I should have called this as k. It's more appropriate to call this as k, because that's what we're taking over here, k plus plus, and I'll say 1 by k square. That's my for loop, and once I'm done with this for loop, I want to print sum, and let me suppress any output for loop. I should start from k equal to 1, says 1 by 0 infinity encountered. K doesn't start from 0, k starts from 1. Let me make the correction and execute this again. I get this number over here. Let me say /n again sum, so it's equivalent to a numerical value. I get 1.54977, which is exactly the value that I get over here when I had this number up to 10. Okay. All right, so that's my little code. Now all I have to do is for the for loop. So for loop is very simple that way. Okay, there are 4 arguments of the for loop: initialization, condition. As long as this condition holds true, for loop will continue to execute the body. If this condition is not true, it will stop. K plus plus, increment k, and this is the body. So initialization, condition, increment, and 4th argument is the body. So body is sum equal to sum plus 1 by k square. So that's my for loop. Now I want to run it for large number of terms. In particular, I want to do this for 200,000. So 200,000, and over here, let me do this again for the table command, and you see that it takes me about 1 second. And I'm going to do the same thing over here for k less than 200,000, and let me execute this, and you see it's going to take some time. It's already more than a couple of seconds, it's still running. It's going to take some time, and that's what I want to show it to you, that for loop is not always a very efficient way of doing things. So yeah, there we go, this execution finished. We got the number that we expected, 1.64493 for the Riemann zeta function evaluated at 2. Let's go ahead and check exact timing for this thing. So what to do that, I'll wrap this whole thing inside this timing command and put a semicolon over here. I'll run this thing. This will measure me exactly how much computational time on this particular computer, on this particular system, it took me to execute this value. From system to system, computer to computer, it can change. In this case, I get the timing over here, it's 10.5 seconds, and this is my value for the execution. So in order to obtain Riemann zeta function, zeta of 2.0, very accurately up to 6 digits, I need to run up to I need to consider 200,000 terms. And in order to do that, if I do it by for loop, which is what many of you who are familiar with programming, you're used to writing for loops like that. If you do write a for loop like that, you see it's not a very efficient way of doing things, and it takes about 10 seconds to compute the same thing. What you could do it over here in 1 second, in about 1 second. Of course, built-in functions that are there in Mathematica, they use some advanced algorithms and advanced techniques to compute those functions, and the series expansions may not be very efficient. But for other cases where you know the series expansion is what you're using, the table command will often turn out to be more suitable than the for loop itself. Now, so does that mean that we should never really use for loop? My general advice is don't use for loop until unless it is extremely necessary. So when is it for loop that is extremely necessary? Whenever we can write table command or some other way of generating the term without invoking for loop, we should always avoid it. For loops are not very efficient, and when should we use for loop? We should use for loops when there's no other way left. That means my decision for this iteration depends on what happened before, what happened in the previous iteration. When it depends on that, that is when I should use for loop. that is, my execution of this step is dependent on the history. When my execution of this step depends on the history, that is the body depends on the history, that is when I should use the for loop. Now over here it appears when I'm executing this command that I need to know the previous sum in order to execute the sum at this moment. I'm adding the increment to the sum 1 over k square. In order to add that, I need to know what is the sum at the previous moment, but that's an illusion, because I just need to know each term in the series, and if I know each term in the series, all I can do is simply go ahead and sum it up. So that's what we did over here, and we found that that was much more efficient. Why? The internal reason is that table commands tries to generate a sequence, so it's acting directly on the in the memory on a list or an array. So it's very efficient that way. It's the processor is working at the level of the memory. It's trying to do the same things again and again. So in this case, it was generating a sequence of 1 over k square again and again, and generated an array in the memory, and that was very efficient. While in the for loop, every time we are executing the body, we are going back, reading, updating k, reading a k value from the memory, incrementing the body, then going back again, and doing this repeatedly again and again. And in this case, it was actually very simple to just simply generate that entire sequence in one go. So that is why table command ends up being more efficiently. Now let's take an example where table command is not going to work, and you really need to know, you really need to find out, you really need to use a for loop. So here's an example. Suppose I need to solve this difference equation, x of n plus 1 equals 0.5 minus 0.5 xn plus log of mod xn. Let's just take this difference equation. Now this difference equation, in order to find xn plus 1, I need to know what is xn. And in order to make this complete, let's say x0 is 1. So we start from x0 equal to 1, and we have to find x1, x2, x3 and so on. But every time I want to find the next value of xn, I need to know what is the previous value of xn. In order to solve this equation, I need to go and write a for loop, because this is something I cannot do with the table command. I cannot generate the entire sequence. I do not know the entire sequence in one go. I have to depend on the result of the previous step in order to find out what's happening now. So let's go ahead and do this by writing a for loop. So here is my for loop. I will go ahead and say, in order to generate the entire sequence, what I'll do is I'll say, x of 0 is equal to 1, that is my initialization, and I will say n runs from 1 to n less than equal to 100. Let's say we want to do this for 100 iterations. Increment n by 1 each time, and coming to the body, in the body I want to find out what is x of n, and that should be equal to minus 0.5 times x of 0 plus log of mod of x, which is absolute value of x of n minus 1, x of n minus 1. This should also have been n minus 1, not 0. All right, so let me go ahead and execute this. This looks like a very nested, complicated structure. Let's go ahead and execute this for loop, and this is going to, the execution of this is done. You can see that if I type x1, x2, x3, I've got those numbers. In order to print the entire series, I'll simply say table xn, and n goes from 1 to 100, and that's my entire series. I couldn't have predicted these terms by writing a simple table command. I needed to actually write a for loop. If you want, you can go ahead and apply a list plot on this just to see how these numbers varied with each iteration. So I'll say joined is true. You see it's some sort of oscillation. So this difference equation leads to some sort of oscillation. In this particular case, I could have not imagined how to do this from a table command, so I had to resort to a for loop. Once again, I can make this for loop a little bit more compact. Sometimes that is useful. but that can also make reading a little bit more difficult. So for example, I can go ahead and I could, in the initialization itself, I could have said n is equal to 1, and I could have added another statement in the initialization part by separating them by semicolons. I could have said x of 0 is equal to 1. Let's go ahead and do this. Let's try this with x of 0 equal to 2. And you can go ahead and play around with it. The important point to note here is that each of these arguments of the for, the initialization part can contain multiple statements separated by semicolons. Again, the condition can contain can contain multiple statements as well, but the last statement should evaluate to a true or a false value. If it is true, it will continue to execute the loop, that is, execute the body and continue to increment. The increment doesn't always have to be n plus plus, it can be anything that you like, as long as it tells you that this is what you mean by going to the next step. So increment can be anything. Incrementation can contain multiple different steps. In fact, if I wanted, I can include this body also inside the increment and left the body as blank. And the body is of course the main part of the for loop where you're executing your main command. As we go ahead and progress in this course, we'll use this for loop for writing code for Runge-Kutta algorithm, Euler's method for solving differential equations, and so on. So this was a brief introduction to for loop, its efficiency, and its comparison with the table command. We'll see you next time.